Hello, welcome to Math School. Today we are going to have a second lecture on geometric progression. Basically today we are going to discuss about sum to infinity and why we are in geometric progression. We are in a different situation which is not found in arithmetic progression, that if we want to add a certain number of terms in AP and GP both are possible, but when it is about infinite number of terms, then actually in arithmetic term, basically the formula actually does not help us. But we have a very special type of formula in geometric progression. Okay, let's see actually what is the situation and why we can do that. All right, so I'm going to share my screen here as usual. All right, so if you see that basically sum to infinity when there is a geometric series like ar squared, ar cubed, you have to have 4 ar to the power n minus 1. Here a is like first term, ar second term, ar squared third term, and this is fourth term, fifth term, nth term. So in geometric progression, when r is less than 1, we know the formula is like this: Sn is a into 1 minus r to the power n 1 by 1 minus r, where r is less than 1. This is the formula that we have just learned it in first lecture. And remember, if the modulus of r is less than 1, then geometric series is called a convergent series. This is a very special thing, different name we see here, convergent. That means geometric series is basically r is less than 1. We can see uh, different values of r where it would be less than 1, but the modulus of r is less than 1 is found in only in particular case. So only in those situations, in those cases, we call geometric progression a convergent series. That means, let us just see some examples, you understand more clearly. Just uh, let's see. Here, example 1. Now we see a geometric series here. The first term is 81, second term is 27, third term is 9, fourth term is 3, and so on. Here, r is 1 by 3. You see the common ratio, r is 1 by 3. So modulus of r is here also 1 by 3, and it is obviously less than 1. So that we just say that when modulus of r is less than 1, then geometric progression will be calling convergent series or convergent simply. So here modulus of r in this series, see here r is 1 by 3. So when you do modulus function on that, the result is 1 by 3 obviously, and it is less than 1. So this GP is a convergent series. I mean example 1. Example 2, we see that the series is like 81 minus 27, then 9, then negative 3, then 1, then negative 1 by 3, and so on. Here r is negative 1 by 3. That means r is less than 1. And modulus of r is here again 1 by 3, and which is less than 1. So this geometric progression is also convergent. Okay, let's see another example 3. Here we see the terms are like 1 minus 2 4 minus 8 16 32 and so on. Here r, I mean common ratio is negative 2, you see, and obviously negative 2 is less than 1, and that means example 1, example 2, example 3. In every case we see the common ratio is less than 1. In first example it was 1 by 3. In second example it is negative 1 by 3, and in uh, yeah, it's 1 by 3, then negative 1 by 3, and then in third example we have found negative 2. So in every case the result of, the value of r is less than 1. But if we apply modulus function here on R, the result is 2, because modulus of -2 is giving us 2, and here it is more than 1. So this GP is not convergent. That means R is less than 1. It may happen, but when you apply more modulus of R, it may not be less than 1. So here, that means convergent series is that series when the modulus of R would be less than 1. Okay, and why we are talking about the convergent series, you will understand it a bit later. Okay, so for every example mentioned in above, the summation can be done for a certain number of terms by using this formula that we know. This formula is used when R is less than 1. As we have seen, the result, I mean the value of R is less than 1 because it is 1 by 3, then negative 1 by 3, then it was -2. So here, every case, the result of R is less than 1. So for summation of a certain number of terms, say n number of terms, we'll use this formula because this formula is used when R is less than 1. But if we look for the sum to infinity, that means summation for infinite number of terms, then we can do it only for the convergent series. Because just example 1 and example 2, we can do it. I mean the I mean to say example 1 and example 2, we can just find the sum to infinity for those series because those are convergent. But example 3, that is not convergent, it's a divergent type series. So here we cannot get the summation for infinite number of terms. So sum to infinity is not possible for the third example because R is less than, R was here, there -2, it is less than 1 though, but no modulus of R is 2, which is not less than 1. So it is a divergent series, we cannot go for it. And now the question is why? Why we can't do that? Now see, there's a simple thing. When modulus of R is less than 1, then R to the power n. So if I put for n, that is infinity, the result would be 0. Now why? Let's see an example. Say R is half or -half. So modulus of R, that is plus minus half, which is less than 1. And see what happens for R. Say R is half, that is 0.5. Now if you put power on 0.5, the result is, when the power is 1, 0.5. But when the power is 2, 0.25. When the power is 3, it is 0.125. That means if you notice one interesting thing, the power is being applied more and more, higher values, but the result is actually getting less. When power is 0.5, to the power 4 is 0.6 to 0.0625, power is 5, it is 0.03125. If the power is 10, then it is 0.00097656. When power is 20, 0.5 to the power 20, which is even less value, very noticeable thing. So when it is power is 0.5 to the power 50, it is very small value. Okay, and if the power is infinity, what will happen then? No one knows actually. Infinite number of zeros will be coming, and where is the n? No one knows. But obviously, you can say it is becoming so small. Result will tend to 0. So that means if we just put when R is less than 1, obviously the formula is Sn is equal to A into R 1 minus R to the power n by 1 minus R. So if you put, because this formula is chosen when R is simply less than 1. Okay. Now if it is the convergence series, so R is obviously a value which is a proper fraction, just like 0.5, 0.2, 0.1, any kind of value. So if as we have seen in this type of value with a higher power, the result is 0. So if the power is infinity, we can say this part becomes 0. So ultimately, what do we get here? You see, so sum to infinity, the formula we get here a by 1 minus r. So it happens when only modulus of r is less than 1. So straight away we can say it is a straight talk that if r is a proper fraction, positive or negative does not matter. If r is a proper fraction, simply remember proper fraction. What is a proper fraction? You remember proper and improper. So proper, that is numerator is smaller always than the denominator, just 1 by 2, 2 by 3, 4 by 5, 4 by 7, many examples. So when r is, remember, fraction, proper fraction, just remember this. If it is positive or negative doesn't matter, but remember if it is proper fraction, then your series is obviously a convergent series and sum to infinity is possible, because if you put the power uh, n onto that, so that but r to the power n will give you always a 0. So sum to infinity's formula would be always this, a by 1 minus r. Okay, thank you very much. I think you have understood when sum to infinity is possible, because there is a confusion among the students that when r is a negative value, so -2, -3, it is less than 1, but they don't understand whether sum to infinity is possible. Actually, because modulus function on this type of value does not give you the value which is less than 1. So it is not a convergent series in that case. So remember this. So only in case of proper fraction r value, I mean the common ratio becomes a proper fraction, positive negative doesn't matter, sum to infinity is possible. So that's all for today. Thank you very much for listening to me. Thank you.